All right, let's talk about section 7.4, graphing rational functions. So we are going to look at more complicated rational functions. Not necessarily that the problems are more complicated, just that there's more going on with the graphs of these functions. So I want to get started by just talking about some rules for asymptotes in general. All right, so for horizontal asymptotes. We've already talked about vertical asymptotes. Vertical asymptotes occur when the denominator is equal to 0. Horizontal asymptotes are going to occur at different places depending on the function that you have. All right. We already saw this a little bit in the previous section, section 3, but here are some rules for identifying where horizontal asymptotes are. What you're going to do is check the degree of the numerator. That's the highest power of x in the numerator. And you're going to check that against the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then there is a horizontal asymptote at y equals 0. It's always going to be at along the x-axis, which is y equals 0. Right? If the degree of the numerator is equal to the denominator, then there is a horizontal asymptote at y equals the ratio of the leading coefficients. All right, so for instance, if you have this function here where you have 7x squared minus 1 over 12x squared plus x minus 7, something like this, you notice that the degree on top is 2, the degree on the bottom is also 2, so you look at the ratio of the leading coefficients. In other words, you look at the ratio, which just means the leading coefficients divided by each other, so it would be 7 over 12. So this would have a vertical asymptote at 7 over 12. Okay? And that's if the degree of the numerator and the denominator are the same. So if you've got a fifth degree on top and a fifth degree on the bottom, you look at the ratio of the leading coefficients. If the degree of the numerator is greater than the denominator, it is not a horizontal asymptote, so there is no horizontal asymptote. Okay, so there's no horizontal asymptote in that situation. That also means that, the asymptotes that are generated can be slant asymptotes, they can be parabolic. There's a lot of different types that can be generated. We're not going to spend a lot of time there. If you go on and take pre-calculus, we'll talk about that more. All right, so let's look at the graph of the function 6 over x squared minus 1. And we will sketch that, and then we will find the domain and the range. All right, so we've got 6 over x squared minus 1. This is what the graph looks like here. Okay, so I have, let's put this up here. Okay, so this is what I've got for the graph. If you want to plot some points, you can. Desmos makes it pretty easy to find important points. So for instance, 0, -6 is on there, so we'll plot that point real quick. Also, vertical asymptotes, before we actually look at the graph here, let's figure out what the vertical asymptotes are. The vertical asymptotes will show up whenever x squared minus 1 is equal to 0. If I solve that, then I can figure out where the vertical asymptotes are. And so x squared minus 1 equals 0, that's a difference of squares. That breaks into x minus 1 and x plus 1. So that will happen whenever x is 1 and x is negative 1. So I can sketch those vertical asymptotes in. Just like with other rational functions, I'm really only worried about the asymptotes and the behavior in between them. So for instance, you could see from the graph over here, we've got this kind of upside down parabola looking thing here with a maximum -6. I'm just going to sketch that in. I don't need to go point for point here. I just need to get the basic behavior down. All right. Now, as far as the horizontal asymptote, if I look at this curve or the function, I see that the degree on top is 0. There's just a constant up there, so the degree of the numerator is 0. The degree on the bottom is 2. Because the numerator is less than the denominator, that implies that the horizontal asymptote will be, in this situation, which will be y equals 0. So we can sketch that in at y equals 0. And then you can see that in the graph too, right? Flattens out to 0 in both directions. So we can write that this graph, or we can sketch the curve in now. So we have that. Have that. The domain is all the x values covered by the graph. So let's look at the domain, and then we'll look at the range. The domain, all x values are covered by the graph except for -1 and +1. All right, so the domain is all real numbers except x can't be plus or minus 1. You could write x can't be 1, comma, -1. Either way is fine. All right, so then the range. The range is given by all the y values covered by the graph. So if you look at the graph, you can see that everything is covered. So you kind of start from the bottom, all right? And you go up until you get to this maximum right here. All of those y values are covered. But then there's this gap that is not in the range. There's no graph right here from -6 to 0. Okay, so here's how we're going to write it. It's going to be y less than or equal to 6. That's part of the range. And then the graph picks up again just above 0. And everything above 0 is in the range. Okay, so the range, then, the other part of it is y greater than 0. So we have y less than or equal to 6 and y greater than 0. Next one. Graph the function, find the domain and range. Same instructions here. So let's look at the function and see if we can figure out some of the parts without even graphing it, okay? So when is the denominator 0? In other words, when is x squared minus 9 0? Well, this is a difference of squares, so that's going to be when x minus 3 times x plus 3 is equal to 0. That's going to be at x equals -3 and +3. So I'll sketch in those asymptotes. Horizontal asymptotes. Well, I look at the degree at the top and the bottom. You can see that the degree on top is 2. The degree on the bottom is 2 as well. So I look at the ratio of the leading coefficients. So the horizontal asymptote is going to be at y equals 2 over 1, which is just 2. So I have a horizontal asymptote at 2. I sketch those into the graph. And then let's just get the function right here. So it's going to be 2x squared over x squared minus 9. So this is what we get for the curve. We tap the maximum there is at 0, 0. So you can put that in. And I should actually, so there's actually a gap here, the curve, between the pieces of the curve here. So at 0, 0 we have a maximum. It goes down like this. And then the other pieces of the graph are up here. Right. So that's what the graph looks like. And then for the domain, it's going to be everything except the vertical asymptotes. So it's all real numbers except x can't be -3 or +3. So x can't be plus or minus 3. And then the range, that's going to be all real numbers except x can't be, I'm sorry, except y. Hold on. Let's do this right here. Okay, so in fact, let's just start. Sorry, I was not even thinking about this when I was going about it. All right, so range is all the y values covered by the graph. You start at the bottom, everything's good, everything's covered until you get to 0. Then there's a gap. So we're going to write that the range is y less than or equal to 0, because it goes up to 0 and includes 0. Then there's a gap from 0 to 2, so that's not in the range. Then it picks up again at 2, and it continues up forever. So we have y is less than or equal to 0, and y is greater than 2. Right? All right, so the last two, we are going to just graph the function, but graphing usually means finding the asymptotes as well. So let's do this. All right. Okay, so let's graph this. X squared plus 3x minus 4 over x minus 2. So when we put this in, you notice the degree on top is 2, and the degree on the bottom is 1. So we won't have a horizontal asymptote here. We have x squared plus 3x minus 4. That's all divided by x minus 2. Okay, and so we have a vertical asymptote at 2. because that's when the denominator is 0, so we sketch that in at 2. And then we're just going to have to look at the curve for the rest of it, okay? So if I look at the curve here and plot some points, or you can trace as well, but you can see that we have negative 2, 1.5, so that goes to like right here. We have negative 1, 2, like that. We have 0, 2 here, and then it's going to come down, so it's going to go something like this. All right, so in this one we did need to use, sorry, I was using the table here. So in this one we did need to use the table sum. All right, and then the other piece, if we just keep moving to the right, we've got 2 is undefined, but 3 is at 14, so 3 is actually off the chart here. So it will come back down, so watch as I add more numbers. So we've got 4, 12, okay, but all of it is sort of off the chart. So this one is sort of weird because it doesn't fit onto the graph, but up here you've got this kind of thing going on. Okay, so there's a sketch of the graph. All right, last one. Try this on your own, and then pause the video, try it on your own, and then see if you get it right. So I'll put this in while you're doing that. So we have 10 divided by x plus 2, x squared plus 2. Okay, so this one is weird. This is what you get for the graph. All right, so the graph has a maximum of 0,5. And then it sort of does one of these things and levels out to be to y equals 0, like that. It's off a little bit, but you get the idea. There's a horizontal asymptote at 0 because the degree of the numerator is 0, the degree of the denominator is 2, so it's got to be at y equals 0. If we were asked to find the domain of this is all real numbers. There's no spot where the denominator is 0. So the domain is all real numbers, and the range would just be from 0 up to 5. I know I didn't ask for that. But you can figure it out by looking at the graph or the function, or both. If you turn this into a table, you can get points. Okay, so you can plot points and get a sketch of the graph. And that is pretty much it for section 7.4.